So Nishit from our team, and today we are discussing binary search. In the last video, we have already covered linear search. So let's start with binary search in this video. Let's give our heading binary search. Binary search. So first thing, note one thing that binary search always works on sorted arrays. Works on sorted arrays. Okay. So first we need to sort. If we have any array, then first we need to sort. Then we will apply binary search on it. Okay. So suppose you got an array. You got an array 4, 3, 4, 9. Suppose 10, 12, 14, 11. Not 11. Let's say 18, 19. So this array is an ascending order array. The smaller elements are at the right hand side, sorry, left hand side, and the greater elements are at the right hand side. So I can say this is an ascending array. Ascending array. Okay. And if I take 19, 18, 14, 12, 10, 9, 4, and 3. So then I can say this is in descending array. Why descending array? Because greater elements are at the start and smaller elements are at the end. Okay. So suppose we sort by, you can say, you do insertion sort if the array is not sorted. We already covered insertion sort video in our sorting algorithms playlist. Please check that out. It was a very conceptual and very understanding video. Please check that out if you didn't. So we first insertion sort the array. It returns us the sorted array, and then we apply binary search in it. Binary search in it. Okay, let's talk about the concept how binary search actually works. Let's first see how linear search works. In linear search, what we were doing that we are traversing every element. We are going from 0 to n. We're checking every element. In the worst case, we are checking every element and we are returning that index of that element with the target element. Okay. So in the worst case, we will go up to n. If there are million elements, then we go up to 0 to million if the target element is the last element. But here in binary search, what we do that we take an average. We take the middle element. Our first step will be to take the middle element. We take the middle element. Okay, we take the middle element. Then our second step, we will check if our target is greater than mid. Then search in the right. Search in right. Okay, search in right. Else search in left. Else search in left. Okay. Then a third case will be that if our target is equals to our middle element, then return the index. Yep. So these are the steps and these are the cases, you can say. Now let's see. Let's take an example. Let's take an sorted array of 0, 2, 3, 9, 12, 14, 17, and 20. So this is the sorted array. Let's suppose our target, what our target is suppose 14. Our target is 14. Okay. So let's use a different color and mark the index. This is 0, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, and this is 7. So our start index will be 0, end index will be, this is the end index and this is the start index. End index will be 7. Yep, end index will be 7. So what it do, we take the average. Our first step is take the middle element. Our middle element will be 0 plus 7 by 2, which is 7 by 2, which is which is approximately 3 point something, that is in integer we say it's 3. So our middle element will be 9. Yep. Then we will check. We have seen the cases if target greater than min. Our target is 14. Mint is 9 greater than 14. Sorry, 14 greater than 9. It says yes. Then move to the right side. We will move to this right side. Okay. Now our array becomes this, where we have to search that targeted element. Okay. So our start from here, our start index become this this one, which is 4. Okay. And our end index will be again 7. And then what we will do, that we again take the mid element, that is 4 plus 7 by 2. 4 plus 7 is 11. 11 by 2 is 5 in integer. We are exceeding the decimal points, the floating points. So it will be 5, which is this. And our target element is 14. Hence, our case will be target equals to the mid element. We will return, the mid element, or the index of the mid element that it is found. So the loop goes from start less than equals to end. A worst case will be that our start index becomes the end index. Okay. if it if the loop gets over, it means the element not found. Element not found. Okay. So uh why binary search is good and linear search isn't? Suppose this is linear search versus binary search. In linear search, what you are doing? You you are going through every element, and your worst case will be that the target element is the millionth element or the last element. Then you goes from 0 to the n. Yep. But in binary search, suppose take this as a tree. Suppose let me copy this array. I will explain you. Let me copy this array first. Copy, paste. Okay. Let me remove these. Let's assume this a tree of middle elements. So our middle element would be 9. So this is the middle element. At the left part, our middle element would be, that is 2. Yep. And in this part, our middle element would be 14. Yep. And our target was 14. Yep. So we will check that is 14 greater than 9. If the 14 greater than 9, search at the right hand positions, the rightmost arrays of 9. So we can discard this part. We don't need to check this, because तुम्हारा 14 ऑलरेडी ग्रेटर देन 9 है, तो देयर इज नो सेंस इन द सॉर्टेड एरे की 9 से पहले तुम्हारा वो एलिमेंट फाइंड हो जाए. Yep. So what we will do, we will remove this. We don't need to check this. And your best case is that the middle element is your target element. Yep. And suppose your target was 17. Then for 14, your middle element would be 17. Yep. Let's take another example. If s greater and yeah, if the start index becomes greater than e, it means element not found. Element not found, because we are iterating from s less than equals to e, and after s becomes greater than e meant element not found. We search till the last index, but the element not found. Okay. So our best case, what would be our best case? That at the first check, we get our middle element as the target element. The target is equals to middle. What it meant key, suppose our target is equals to 9. So at the first middle, when we are taking the first middle, we get the answer. We will return 3 here, and that's how the fast it is. Let's take about the comparison. How many comparison we are doing? Suppose this is an array, okay, of n which have n elements. We take the middle element. Either we go left or we go right. Suppose we go right, you can take that in left also. But suppose let's go, then our searching part will becomes n by 2. Yep. Then again we take the middle element. We either go right, we either go left, and our searching part becomes smaller, which can be n by 4. Yep. Then again our searching part becomes smaller and it becomes n by 8. So you can see a pattern in this. When our start index, or you can say they are step at step 0, it is n upon 2 raised to power 0. This was the step 0. When a step 1, can we say it is n upon 2k? Yep, it is sorry, it is n upon 2 raised to power 1. At step number 2, can we say it is n upon 2 raised to the power 2? Yes. At the step 3, can we say this is n upon 2 raised to the power 3? Let me make it smaller such that you can see this. So suppose we get up to the kth level. This is the kth level, or you can say rth level. So it becomes n upon 2 raised to power k, 2 raised to power r. Yep. Let's suppose a best case with 1 meant n upon 2 raised to r equals to 1. Yep. That meant n is equals to 2r. Our best case is 1. Our best case is first step. So this is, let's take log. It becomes this r log 2, and the value of r will be log n by log 2. By using the property, we can say it is log base 2 n. Yep. And see how binary search is so much fast than linear search. Suppose you have like 10 million 10 million elements in an array. In the worst case, what linear search will do, it goes from 0 and up to 10 million. Yep. But in binary search, what happens, it goes up to log base 2 n. What is log base 2 of 10 million? Let me find this. What is log base 2 for 10 million? Log base 2 calculator. It is 10. It is 23. It is approximately 23. When our in linear search, the worst case is it will take 10 million comparisons. It will take 10 million comparisons. Whereas in binary search, it just happens in 23 comparison and we will get a result and the targeted index. So how fast is this? You can see this from here. Let's again take an example. Again takes an array. Let's take a let me that is 2, 4, 6, 9, 12, 15, 14, sorry, 18. Okay. Our start index will be 0 and the end index will be the length minus 1. Yep. Take the mid element. Our mid element will be 0 plus the length will be 1, 2, 3, 4, 5, 6, 7. That is length minus 1, that is 7. So 0 plus 7 by 2, which is 3. 0, 1, 2, 3. This is the middle element. So अपने को अब क्या करना है, if the targeted element, by the way, these are for ascending order. If you just go for descending order, your the conditions becomes opposite. So if target is greater than is equals to middle element, you have to set your start equals to the the index of the middle element plus 1. Else you have to set else you have to set start sorry end is equals to middle minus 1. Why we are doing this? Let me tell you why. We get the middle element. If the middle element is smaller, then we go to the right side because the targeted element will be bigger, and our mm, the searching part will become this. So we have to shift our start index to this. So we are doing mid plus 1. Whereas if we are going to the left, suppose our targeted element will be 4, then our end index will be this element, because our searching part becomes this. That's why we are doing this. And this is for the ascending order. And for the descending order, you just need to swipe, because it depends. If you sort the array in ascending order, you have to just do this. Else you have to swap this or change the conditions. Yep. Let's take our or descending order. Suppose 14, 9, 7, 3, 2, 1. Okay. Suppose a targeted element is equals to 9. Yep. A targeted element is 9. A middle element will become 0, and it 1, 2, 3, 4, 5. So a middle element will be 0 plus 5 by 2, which is equals to 2. That is this. Okay. Is the target 9 is greater than 7? For the descending order, we will do end is equals to mid minus 1. Yep. When the target is greater than mid, you can see when it is in ascending order, we are doing this and start equals to mid plus 1, and else we doing this. But in descending order, we are setting the end value to mid minus 1. Same, the else is equals to start plus 1. Sorry, mid plus 1. Okay. So that's a binary let's search. Start writing a binary search program. So let's declare the function for binary search that accepts an array of integers, accepts the target, and accepts its length. Yep. Or you can just accept the length. Now we need how many variables? We need a start variable, we need an end variable, we need a mid for the middle elements, and we need a target variable for the target to show the target element. So we need start that starts from 0, and we need end that starts from length minus 1, that is n minus 1, because n here is the length of the array, and we need a mid variable that stores the middle indexes, and we need a target. Let's take the input of the target element is, that is scanf percentage t and target. uh, in the notes we have seen that our loop will run till start becomes greater than end. Yep, that means our loop run until this valid start is less than equals to it. Yep. Yep. Now we calculate the middle element, that is 2 into start minus end minus start by 2. Why we are doing this? Because at some point, suppose you have million of elements, you add them, it can exceed the range of integers. So instead of adding start and end, we just supply we are doing just or you can say no, it's wrong. We will do start minus end minus start by 2, because start plus this. Yep. Because when you take LCM, the 2s minus, let me comment it out, the 2s minus end minus s whole is nothing but 2s minus s is s, that is s minus n by 2. Yep. So instead of writing it directly, we just um, write it little simplified, you can say, or that that will not throw an error. So uh, our first are the best we are the best case. What was the best case? The best case was that the middle element becomes the target element. Then we have to return the index to the middle element. Yep. Then if it's not, we have to check whether it is ascending or a descending element, descending array. So how we the array of start is greater than array of, or you can say array of n, then it means that it's an ascending array. That is mid equals to, no, you check if array of mid is, using target is greater than array of the middle index, then what we do, if the target is greater, then we have to shift to the right. That is start, we have to shift the start pointer to the right side, that is mid plus 1. Else we have to do end equals to shifts to the left position, that is mid minus 1. And for the descending part, for the descending array, what we have to do, if target is greater than array of mid, we can just copy paste and change the conditions. If the target is less than array of mid, you just have to move the start pointer to the right hand side, because the smaller elements are at the right hand side. So that is it, and we'll return mid. If anything, if a start exceeds the end, meant start is not remains is equals to the end, then we have to return minus 1. That means the element not found. Yep. Let's do binary search. Binary search of array of element 9, sorry, 9, length 9, and we just print binary search array 9 percentage t index. Okay, let's run this program. um, First compile this one, that is gcc this, then I say binary. Let's insert the elements. Let's take the same example we took that in the nodes, that is 2 4 6. The first element is 2, second element is 4, then 6, then 9, then 12, oh sorry, 112, then 13, then 13, 90, and 9. It gets the array sorted by insertion sort. Our targeted element would be, let's say, 90. We got the seventh index, that is 0 1 2 3 4 5 6 7. We got the seventh index, and that is binary search. And we'll see you in the next video. See ya.